So we're ready to go. Okay, again, good morning or good afternoon, everyone. Welcome to APNIC eLearning web class. And this is the second e-learning that we are conducting for today. As you know, Wednesdays are e-learning Wednesdays for APNIC, and we conduct 4 sessions, different topics, all about internet technologies. For this afternoon, our coverage is on BGP. We will be doing BGP Basics for this class for 1 hour. And then later on, during the 4th session, there is also BGP Attributes. But let's focus more on BGP Basics for the time being. Now, before we move on to that, I'd like to do some housekeeping things first. So today is the 19th of March in 2014. It's 12:30 in the afternoon from Brisbane in Australia, where I'm broadcasting this class. And of course, I'd like to introduce myself very briefly. My name is Cheryl Hermoso. I work for APNIC. APNIC, as you know, is the Asia Pacific Network Information Center. It is the Internet Registry for the Asia Pacific region. Now, I am part of what we call the training team, and we do conduct face-to-face trainings, workshops, tutorials, trainings like these, e-learning sessions for the members of the Internet community, with topics concentrating on Internet technologies, Internet resource management, routing, BGP, DNS security, network security, and of course IPv6. Now for this class, this will be for 1 hour, and I'd like to remind you that by the end of this session, I will be asking you to fill in a survey for me, just a very quick one, so that we can get some feedback from you of the quality of this session, and also if you have any other topics possibly that you're interested in, and if we can do it maybe in the future, we can add that up to our curriculum. So what are we going to cover? Now, this is just a brief overview of what we are hoping to be covering. Now, this is actually, this is a technical topic, right? Our aim is going to people who wish to advance their technical knowledge of networking. Some of you may have intentions of maybe implementing BGP on your networks. Maybe some of you already have. Some of you may be maintaining their own IP networks, but not essentially or not exactly BGP. Or some of you may just have some general knowledge or general interest in the topic, but have yet to actually dive into any implementation of sorts. So our discussion requires that you have somehow a fair amount of understanding of routing, but we will have just a very brief overview of what routing is and all that. But yeah, some terminologies we will try to recall and explain if it's unclear. So if you have questions on that, let me know. But of course, our main focus is on BGP. So what exactly is BGP? What are the features? Okay, what is path vector protocol? So BGP is a type of a path vector protocol. What are some of the common terminologies that we use on the internet, such as peering and transit? What are the difference between them? How does BGP operate? Okay, what are the different stages that are required? Some attributes. Now, this attributes part I'm not going to cover in much detail because we have another e-learning session that covers exactly that. But it's just a fair introduction so as we have an idea of what it is. And lastly, how do you add prefixes? How do you actually announce prefixes so that your networks are can be seen on the internet? So we'll try to do that. That's quite a hefty list of topics to cover, but we'll see. We'll try our very best to finish that in 1 hour. Now, I have a tendency to talk quite fast sometimes. I'm not sure if I'm going to do that now, but just in case you have a hard time understanding myself, just please let me know using the chat. As much as possible, I like the class to be interactive, so as I know that I'm not talking to myself. So if you have anything, any feedback, anything that you want to add, maybe some experiences of yours with regards to the topic that we are covering, please feel free to post them on the chat window. All right. With that, we'll dive ahead and start with the very common question, what is BGP? So before we do that, what exactly is routing first? As you know, routing is it's a process of two things. It's routing and both forwarding. So it's a process of forwarding packets between networks. It uses a layer 3 device. It can be a router, it can be a gateway. So as I've said, it has two things. It has to have a list or a map of the destinations that it needed to go, before your packets can actually be forwarded. Now with BGP itself, it's a routing protocol that is used to communicate, okay, or to talk in between different networks. So these networks are autonomous with each other. If you look at the RFC 4271, which gives us the actual definition of BGP, it says there, and I quote, the Border Gateway Protocol, I had to look it up because I can't memorize that. It's an inter-autonomous system routing protocol. So you are talking between autonomous systems. Now, what is an autonomous system? We will answer that in the next few slides. The primary function of BGP, or a BGP speaking system, is to exchange network reachability information with other BGP systems. So what is network reachability? So this network reachability information includes information such as a list of the autonomous systems that reachability information traverses. This information is also sufficient for constructing a graph of the AS connectivity for this reachability, and for which you can find out, or you can see routing loops, and you can prune these routing loops at the AS level. And also, you can have some policy decisions and enforce these decisions. So out of that definition, you can see three terminologies popping up. You have a list of autonomous systems, you have routing loops, and you have policy decisions. So deeper understanding of these terminologies will come naturally as we proceed. So simplify the definition. BGP stands for Border Gateway Protocol. It is one of the number of routing protocols that we use to route information packets in and out of our system, in and out of our network. Okay, routing is concerned about finding the best path to a destination. Okay, simple as that. So I've said you need to create like a map. In this case, that map is, we're using the list of autonomous systems. So this is what we need for reachability information. There are two general types of routing protocols. You have the internal and external, IGP and EGP. Examples of IGP are, of course, RIP, EIGRP, OSPF, ISIS. The other type for EGP is what we use for our main concern here. Okay, it's the exterior or external gateway protocol, or EGP. The first, and of course until now the only EGP example that we're using, is the Border Gateway Protocol. So then, going back to the definition, it says that Border Gateway Protocol is a routing protocol used to exchange information between different networks. Okay, let's define what we mean by different networks. All right. Now, BGP is also considered as the most useful routing protocol. Usually, we also call it or refer to it as the Internet Routing Protocol. Why? Because it is very essential, okay, for the internet. It essentially runs the internet. Now, the standard specifications that you will want to look at that covers the specifications for BGP are described in RFC 4271. You also have two other things, RFC 4276, which contains an implementation report, and RFC 4277, which is, it might be more useful for you if you are actually using BGP. So RFC 4276 is if you're interested in writing the software. But RFC 4277 is for implementation. Okay, so most of us that have more operational experiences in using BGP might want to look into 4277 rather than 4276. Now, moving forward and discussing more of the characteristics that are associated with BGP, let's look at some of the features. Okay, BGP features. First and foremost, BGP is a path vector protocol. What is a path vector protocol? We have many different common classes of routing protocols. We have distance vector, we have link state routing, we have path vector protocol. OSPF and ISIS, they are both IGPs. They are using link state routing protocol. BGP, on the other hand, uses path vector protocol. You can think of it as a bit like distance vector protocol. Distance vector protocol is concerned with hops. Okay, it's concerned with reaching point A to point B using how many hops. But rather than the number of hops, in path vector protocol, this is a simplified definition, of course. In path vector protocol, we are using what we call as an AS path. Okay, AS path, so the path or the list of autonomous systems that it needs to traverse to get from point A to point B. Another feature of BGP is it's sending incremental updates to peers. So BGP uses incremental updates, which is very strategic to conserve bandwidth and also to conserve processing power. This is, well, let's say, after the initial exchange. So first, if you don't have adjacencies yet, you'll need to exchange the complete routing information. So you have a pair of BGP routers, they exchange these complete routing information, but thereafter, okay, any exchanges that will proceed between them are only about any changes to these information. Such an incremental update design requires, of course, a reliable means of transport between those two pairs of BGP. Okay, that's why in BGP we are using TCP. It runs over TCP using port 179. BGP routers talk to each other using these permanent TCP connections. Now, another very good thing about BGP, of course, is you are able to enforce policies. As you know, BGP is an inter-AS protocol, meaning that in your network, in your autonomous system, you have certain policies. These are based on your organization or your business requirements. Let's just say that, in my network, I've decided that I only want particular types of traffic to come into my network. Or I only want to peer with these neighbors and I will only send them, the prefixes that I currently have, I will send them only to these particular neighbors. Or for my outgoing traffic, I want my internal users to only access these particular services. So using these requirements, our internal policies, we can set up, where there are many options for these policy enforcements in BGP. You can select the best path, you can select the best routing policy, you can create them, add them onto your setup. One of the main features of BGP is its ability to control any incoming or outgoing traffic. We call it as an ingress or egress traffic. Since BGP is implemented in the border routers, these border routers stand between the network and your neighboring networks. This is where we create policies. This is where we control any of our ingress and egress traffic. This is where we can define the type of traffic that we want and from which IP prefixes are allowed, of course, to enter into our network. Now, BGP chooses routes using an algorithm. It's a deterministic algorithm that assesses the path attributes and, of course, chooses a very efficient or the most efficient route that will avoid both routing loops and will avoid conditions. Now, the way that you select these routes, can also be controlled through a set of your BGP policies. You specify them, you create them, add them in your configurations. Whether you can choose whether your AS is willing to carry traffic from other networks as well or not. However, BGP cannot tell you or cannot guarantee the most efficient route to any destination, because it cannot know what happens within each AS. It can only compute for so much. Anyway, we'll go to more details of that later on. Now, BGP is, of course, using classless inter-domain routing or CIDR. The current BGP standard, BGP4, implements this. What is CIDR? It's essentially it's a set of rules for IP subnetting that allows you to summarize any groups of IP addresses. So here we're using classless routing, classless addressing. Before we're used to doing classful, class A, class B, and class C. Now with classless addressing, we can use any IP addresses, of course. And if you have adjacent blocks, you can summarize them as one. You can say you have 2/24s that are assigned to you, they are adjacent, or you have a big block that you've assigned to your customers. Maybe you have like 100 customers, and each of them has got a /24. Now, you don't necessarily have to announce each of them to the internet. You only need to aggregate all of them into one aggregate block, and you announce them instead of 100 separate network prefixes. Okay. Of course, one reason for that is you don't want the global routing table to be very huge, and you don't want um, to be adding to that. Now, BGP is widely used for the internet backbone. As we've said, it is mainly considered as the internet's routing protocol, and of course, it works with autonomous systems. Now, just a brief overview of what or how path vector protocol works. As I've said, it's used for interdomain routing protocol as compared with link state protocol and distance vector protocol, both of which are intra-domain protocols. With path vector protocol, it works between autonomous systems. Okay, the important thing to note here is with path vector protocol, it relies on AS path. Okay, it creates a route, or what you can say as a sort of like a direction of autonomous systems that your data will have to traverse from the source going to its destination network. Okay, it's, as I've said, it's somewhat similar to distance vector. Okay, but instead of using hops, you're using AS path to reach its neighboring routers. Now, I think I might have an example here. So let's look at this diagram here. For example, you have these many autonomous systems, these different networks. Now, an autonomous system, of course, is a well-defined set of network that has two features. One is it's normally under the same administrative control, and the next one is it should have the same policy all throughout. Okay, so in this case, we have defined 6 autonomous systems. An AS is defined by a number, a unique number called an autonomous system number, or ASN. So that's why you see different ASNs here. AS6461, 7018, 11268. They are all autonomous system numbers. They are all networks, autonomous networks, and they are now exchanging prefixes with each other using path vector protocol. So if AS6461, let's say I have a traffic that's going to AS11268, maybe it's announcing a certain prefix, maybe it's announcing 203.176.189/24. How do I know about that? It's a series of announcements and acceptance. Okay, each autonomous system will have one speaker node. We've already called it earlier. It's called a border router. The border router creates a routing table. It advertises these learned routes to its neighbor speaking routers. So in this case, 6461 announces prefixes to 7018 and AS600. AS7018 announces to the next one. AS6337 announces to the next one. So again, it's a series of announcing or advertising routes and also accepting routes. Once AS6461 announces a route to 7018, 7018 must accept these routes in order for him to also forward that to his other neighbors. The decision to either announce other networks' AS or other networks' prefixes depends on a lot of things. Most notably, it depends on an agreement or a connection between your networks. So to understand this more, let's look in the next slide some of the terminologies that we associate with BGP. So these 3 words, it defines, I have here, it defines the way or the arrangement between operators that carry the traffic and all the routing information, of course, across networks. So these terms are transit, peering, and somewhere in between is default. So what's the difference between transit and peering? A lot of operators would have confusion, or advertising wise, they have a tendency to use one over the other. They're mostly used interchangeably as well, but there are differences between them. When you say transit, it's both about carrying traffic across networks, but when you say transit, it's carrying traffic through a network, but usually for a fee. So you have transit providers. They give you internet access. They give you, say, a certain bandwidth. You subscribe to them. You pay them on a monthly basis or a yearly basis. It costs you money for your traffic to pass through their network. So small providers may be getting transit from a larger internet provider. These larger upstream providers get them to from tier 1, tier 2 ISPs, and so on and so forth. Peering, very closely related to transit, okay? It is also used to exchange routing information and thereby used for exchanging traffic or forwarding traffic, but usually it's without a fee. You have routers, they are peering with each other, okay? These are networks that have some form of agreement, some form of what you call as a settlement-free peering. There's an agreement between them. They're peering with each other, exchanging routing information with each other, but it doesn't come with a cost. There might be a small administrative cost just to maintain the infrastructure, but that's it. Okay, the reason you're peering with each other is because you're both benefiting from it. Okay, maybe it's because there's a lot of traffic going on between these two networks, and it's easier to just peer rather than letting them go through their upstream and pay for for bandwidth and also just to get to the other network. Also, it's for latency purposes. Let's just say that you have two big ISPs in a certain country or a certain economy. Okay, now I am going to send a message perhaps to another person, my friend, who is using services of, say, provider B. I'm with provider A. If you don't have any peering within, say, our country or our locality, then all traffic will be going via our upstream. Most likely it will be going outside of the country before it goes back to provider B. So as a result, I'm paying my upstream, and also the traffic takes longer to reach its destination. So that's one reason. That's actually two reasons for peering, okay, cost-wise and also for latency purposes. So you peer with each other because you're both benefiting from it, right? Now the third one is default. Default is where you send your traffic when there is no explicit match in the routing table. Now we've said that in order for you, okay, to send a message or a packet to an IP address, you should have an information of where to send that packet. Like I have a block of IP address on my routing table, and my next hop will be this router. Okay, if I'm using explicit routing, that means that I have a list of all the IP prefixes and how to send it. Okay, I have a complete information, okay, of the rest of the internet. That is the explicit routing. Now, the other end of that line is default. If you don't know, if you have an idea of where to send the information, you have like just one provider or one link that will become your default. Everything that I don't know, I'll forward to a default. Normally, that is our ISP, our upstream providers. Okay, it points to the default link just in case, and it's basically our gateway to the rest of the internet. If we're not specifying a certain route entry in our routing table, then the packet goes to the default. Now, something very related to that is DFZ, or the default free zone. We've talked about explicit routing. If you have a complete list on your routing table of the rest of the internet, meaning all the prefixes that are announced, then you are actually in a default free zone. So default free zone is or are routers which have explicit routing information about the rest of the internet. I don't need a default route, okay? I don't need that backup line that says if I don't know, it goes through here, because I have information of the rest of the internet. That means having a list of the entire global routing table, which right now is at about 450,000 prefixes. Now, a bit more about prefixes in transit. So we already have the definition, but this is just an example. This is just a diagram that shows us how it is. So here you have two providers, provider A and provider B. Both of them are connected to an exchange point or an IXP. Okay, Provider C and provider D are also connected to another IXP, an exchange point. An exchange point is normally where you do peering. Okay, this is peering, this is not transit. However, if you have traffic that goes between these IXPs and there is no other way, okay, to connect them but through provider D, then that is considered as transit. Okay, A and B are peering with each other, but they both need transit for any traffic that goes to provider C. I think you already know an autonomous system. We have somehow defined this in the previous slides, although it's not actually in any of those slides. But an autonomous system is very important with BGP. Okay, it's the fundamental unit that we work on with BGP. In fact, BGP relies heavily on autonomous systems. We said it uses ASPath, right? It's a list of these autonomous systems or autonomous system numbers. BGP sees the network or the entire internet as an interconnection of these autonomous systems. So what's an AS? By definition, it's a group of networks, okay, that operate under the same routing policy. So an example of this is if you have a multi-home providers network or the customers network. Each of these autonomous systems also has a unique number called an ASN. It's either 2 bytes or 4 bytes. It's a unique identifier. It allows your AS to exchange dynamic routing information with other autonomous systems. Okay, that's basically what BGP uses to do its exterior routing. Yeah, you can say that perhaps BGP is like the fundamental unit or the cornerstone of BGP. We've defined what an autonomous system is. It's actually just a number, but just note the range of these autonomous system numbers. We have two types now. We have 2 byte AS number and 4 byte AS number. 2 byte is 16-bit, so if you convert that into decimal, that's from 0 to 65535. 4 byte, although technically consists of everything from 0 all the way to 4.3 billion, okay, just to distinguish between 2 byte and 4 byte, we usually call 4 byte AS numbers as the one starting from 65536 to 4.3 billion. There are two ways which we represent 4 byte AS numbers, okay, because with 2 bytes we're used to it. Okay, we see AS1, AS2, AS65535, all of them are 2 byte AS. Okay, with 4 byte, some of them are quite big, like 4.3 billion, 42940. Do you really want to write it down? For some reason, because of that, they have AS dot. Okay, so your range will be from 1.0. So essentially what you're doing here is you're splitting up your 32 bits into two 16-bit, okay, groups, and then convert that into decimal. Okay, so your 4.3 billion here, okay, is actually 65535.65535. Okay, all 116-bit is 65535, and do that for the other one. We don't actually recommend using AS dot. Okay, in our region, mostly we use AS plain, so we'll just stick with that. All right, so those are the essential factors, essential things that you needed, okay, for BGP. So we've covered autonomous systems, we've covered the different types of BGP, we've covered the different terminologies, peering and transit, that are important factors with how BGP works. But how exactly does it work? What is a general operation? I'll be showing some diagram here in a few while, but essentially, when you create a BGP internetwork, okay, you have designated routers. These designated routers are what we call as BGP speakers, and they speak the BGP language. One of the most important characteristics of BGP is its flexibility. Okay, it can connect together with any internetwork or any autonomous systems using any arbitrary topology. The only requirement is that each AS will have at least one router that runs BGP, so it's like the BGP speaker, and it is connected to at least one other autonomous system or another router that also runs BGP. Okay, and yeah, you just follow it up. You have like a web of these BGP speaking routers. So to actually create a BGP internetwork, these BGP speaking routers or border routers are physically connected. Need to have direct connection. Okay, at least of course one connection to another BGP speaker in whatever topology that you have. We call these BGP speakers in another network, another AS, we call them as our neighbors. Okay, so we are all BGP speakers. We have direct connections to our neighbors. We exchange routing information about our network and about the rest of the, say, other networks that are connected through us, okay, to these neighbors. The direct connection between them allows us to exchange routing information about other ASs in which they are of course part. So basically, in I think let's look at these example here. We have this is quite a good example. BGP speakers AS100 and AS101. So you notice that for AS100 we have two BGP speakers. For AS101 we have two BGP speakers, okay, and one for AS102. We said that in order for you to talk a BGP with another router, it has to be between, okay, two border routers which are directly connected to each other. So you see that here, A from AS100 is connected to router C of AS101. Same with router B, D, and E. They also have direct connections, right? So that's essentially how it works. You have peering, okay? Peering is done on point-to-point links between the shared media. Some terminologies, we've talked about neighbors. Neighbors are basically just your adjacent autonomous systems which you have direct connections with, which you are speaking BGP with, which you are exchanging router information with, right? So these are adjacent routers that you exchange routing information. Now, in order for you to get and receive information, it has to be announced. Announcement is sending the routing information out to your neighbors. Okay, again, that depends on the agreement between you, like which prefixes are allowed, etc. Now, you also can originate. Okay, so if you announce, it has to be accepted, but this announcement doesn't necessarily have to be coming just from yourself. Okay, it can be something that's announced by someone else, and then you received it, and then you are announcing it forward. But originate is when your AS is the origin of the announcement. If you have a prefix that you probably get either from the RIR, from APNIC, or from your upstream provider, and you are now going to announce it, okay, you are inserting, okay, you are adding another route entry into the global routing table that is originating something. That's originating a prefix. Okay, you also have peers. Peers are routers within one AS or within neighboring ASs as well that you exchange information with. You have iBGP and BGP. So you actually just don't implement BGP on externally between BGP speaking routers. It can also be propagated within a network. That is what we call as iBGP. You only do iBGP, okay, so that you can propagate the prefixes that are learned from outside, that are learned externally, and propagate that within your network, okay, within the same autonomous systems. These neighbors do not have to be directly connected. However, okay, we'll need to set like a full mesh setup in between all your routers that are going to exchange prefixes via iBGP. With eBGP, on the other hand, we know what it's for. It's what we're commonly used to when we're referring to BGP, and it is within the neighbors. And to have peering with these neighbors, it has to be directly connected. Okay, so just notice the difference between iBGP and BGP there. For iBGP, you don't need to have direct connection. With eBGP, it has to be directly connected. Okay, now BGP attributes. We said that we are essentially, with the core functionality of BGP is to exchange routing information, right? Now, there are some parameters, there are some properties that would help them define, okay, the best path among the many possible values that it receives. So routes that are learned via BGP have associated properties. These are used to determine the best route to a destination. For example, there are multiple paths going to a particular destination. Say, from router A to router D, you have probably 2 or 3 possible paths. Okay, 2 possible roads to get there. But what is the best one? These properties define that, and they are called as BGP attributes. Okay, each route prefix has an associated BGP attribute. These include, of course, useful information about the route, where it came from, how to reach it. So there are 2 types. We have well-known attributes. We also have optional attributes. Well-known attributes can be mandatory or discretionary. So well-known attributes are supported by every BGP implementation. Some of them are well-known, some of them are mandatory, meaning it's necessary. It has to be included in every route entry, but some of them don't. These are what we call as discretionary attributes. The ones that are mandatory are the following. So origin, so where it's coming from, how your BGP router responsible for originating the route first learned of this. So what is the origin? What's the AS path? Again, that's the list of ASNs that has to be traversed. You have next hop, which carries the IP address of the first BGP router along the path, okay, where I will forward the packet if ever I receive one that is going to that destination. So by default, this is actually the router that announced that prefix to myself, but that is not always the case. You also have local preference, local prefs. This information is only made available or distributed inside of an AS. Okay, now routers, of course, use this number to allow the network to favor a particular exit. So this can be used for engineering your traffic. If you want your traffic to go or to prefer a certain exit point, okay, maybe you have like 2 upstreams, but you want a more reliable connection using provider D. Okay, so you want most of your traffic to go there, so you can set values for local prefs. Okay, again, this is only distributed inside of an AS, not outside. With well-known discretionary attributes, as opposed to the mandatory one, which has to be present in every route entry. With discretionary, it doesn't have to be present, but your BGP router must be able to recognize it. Okay. There's also optional attributes. So that's the other end, which is not well-known must be supported, right? But optional doesn't necessarily have to be supported by all BGP implementations. It can be there. It may not be there as well. When you receive route entries, you don't necessarily have to understand all of it. Okay. Optional attributes are either transitive or intransitive. So there's a special flag there that tells you whether it's using transitive or intransitive. So with transitive, even if I don't understand a certain field or a certain attribute, I'll have to forward it. I'll have to pass it on. Okay. But if it's intransitive, if I don't understand a specific a parameter or a specific attribute, what I do is I will just drop them. Okay, and again, any unrecognized non-transitive options will be dropped from the route information. Okay, so yeah, these are just like categorization of these BGP attributes. But what's most important is to understand what these actual attributes do, like origin, AS path, aggregate, community, MEDs. So what are they for? As I've said earlier, they can be used to tell you what will be the best path, and you can manipulate values of these BGP attributes to help you, okay, of course, engineer your traffic to prefer certain exit points and to prefer certain entry points. Okay, now this is like the BGP IGP model, and most ISP networks, when they use BGP, when they use IGP. Okay, so with BGP itself, as I've said, it can be used internally and externally. We've got iBGP and you've got also eBGP. So it's one protocol, but the function is split into two. iBGP, we've already discussed, is mostly used to get prefixes from outside, okay, and distributed within our network, okay. But eBGP is exchanging prefixes within other autonomous systems. Now this model shows us it's like you have like 4 different buckets, 4 different autonomous systems. It just tells us that even if you have an IGP, so what is an IGP? An integrated protocol. You can be running either OSPF, you can be running ISIS, you can be running older protocols such as RIP or EIGRP as well, although we don't recommend it. So your main option really here is to use OSPF or ISIS. So that is your IGP. Now, you also have to run both iBGP and eBGP. iBGP within your network, okay, to carry prefixes across your backbone, across your internal network, and maybe going through your customer prefixes. But eBGP is what we know, it can be used to connect or exchange prefixes with other autonomous systems and implement certain routing policies between yourselves. Okay, we've already somehow looked at iBGP. She said it's preferred internally. Now, if you look at internal BGP, the rules are a bit different, right? We know that what it's used for. We know that it doesn't have to be directly connected, which we do with iBGP. But if it doesn't have to be directly connected, what do? It should be full mesh. It should be running full mesh. iBGP speakers must be fully meshed. So if you have, say, 5 routers, okay, that have iBGP or running iBGP, okay, you should have connections from router 1, because your configurations, you just do this in your router configuration. Router 1 to router 2, router 1 to R3, R1 to R4, R1 to R5, and cycle goes on. So the result is you might have very huge amounts added onto your configuration if you have a lot of iBGP speakers on your network. What if you have 100? What if you have 1,000? Although it's not recommended for you to have possibly more than 10 routers in iBGP, but configuration-wise, if you do that, okay, again, your configuration will explode. What else? So another thing about iBGP is it is implemented in using loopback interfaces. So see here, you have iBGP, you have 4 routers speaking iBGP, A, B, C, and D. Okay, you want to say you have direct connections, as you can see on the red ones there. But why do we implement iBGP on loopback interfaces instead of point-to-point links? Of course, we can run it. I think another sample is here. You can run it on point-to-point links. No one's stopping you from doing that. But what happens when the interface goes down? Okay, the iBGP session between router B and router C in this case. So you have 3, router A, B, and C. So let's just say that from A, you're sending something to C. But what if this link, any point-to-point link here, maybe this interface or the interface from router C goes down? You have another way, and that's using B. And you can find that out using dynamic routing. Okay, if you're using point-to-point links, then you can see this down, but there's no way for your traffic to find other alternative paths. Okay, so that's why we're using In this case, we are using the loopback interfaces. So run iBGP on loopbacks or the logical interfaces because it is always up. It's a virtual interface. There is a command in iBGP, in BGP basically, it's called neighbor update source. It allows the BGP process to use maybe a specific IP address or maybe a specific interface as the source IP address. So in this case, we will set neighbor update source as our loopback interfaces. Alright, so constructing the forwarding table, so it typically works like this. You have a BGP in process, you have a BGP out process. For BGP in process, the BGP speaking router will of course receive path information from all of its peers. BGP does path selection process and then it places it in the BGP table. So you actually have a lot of routing tables within your router. You have one for each routing protocols, and with BGP you have let's say a routing table and it will be forwarded to a forwarding table. The forwarding table consists all of the best path. Okay, so essentially it will your router will do the path selection process. It flags the best path, okay, and then forward that using an out process. The BGP out process is the way to announce what is the best path information going to its peers. Okay, so I've said the best path is stored in the routing table. Then the best path among all these different routing tables are passed on to the forwarding table. All routing protocols, BGP, OSPF, ISIS, all the connected routes, also all your static routes, all these information are stored in routing tables, but only the best path goes to the forwarding table. How do we know which one's the best path? Okay, if its prefix length is unique and it depends on the metric associated with the routing protocol, okay, or what you call as the protocol distance. So there's a way for it to compute what is the best path. Now to just illustrate that, it's something like this. So you have an in process, BGP processes which ones will be kept, which ones will be discarded. It goes to the BGP table, and that BGP table containing the best path after running through the process goes out to its peers. Now this BGP table is forwarded to the routing table and the best path will be added to the forwarding table. Okay, so essentially all the best paths are kept in here. Questions so far? Alright, so where are we now? eBGP. So eBGP is basically in between routers, BGP speakers within different ASs. It should be directly connected. But one important thing to remember here, which it's a design issue. It's a it's something that most newbie engineers would have problems with, is running an IGP between eBGP peers, or more specifically, if you talk about an ISP setup, if you have customers, we somehow include these customer networks as part of our backbone, okay, as part of our network, which it shouldn't be. Okay, these are different networks, and therefore, okay, your customer network must be separate from your internal network. It's running different autonomous system, right? It's basically a separate network, and you can even have different policies in between them. So never run an IGP between eBGP peers. Okay, now how do you configure BGP? I only have Cisco IOS as an example here. You have to, of course, specify, okay, the AS number. Okay, for AS numbers that are greater than 65535, which are using 4-byte AS number, you can either use AS plain, which we recommend in this case something like this, or you can use AS dot. So I've already explained how it should be done. So just have a look at that. This is how it looks like. You specify, of course, your neighbors. You have to know who you're peering with. So in this case, we have router BGP 100. 100 is our AS number. So we will set up peering with another router, another BGP speaking router in AS101. So you'll have these lines. Neighbor, the IP address of the neighbor, remote AS, its AS number, and then we specify filters. Okay? In this case, we've created some prefix lists. So this contains possibly a list of IP addresses or IP blocks that we're allowing in and out of our network, okay, coming from network C, okay, coming from AS101. Okay, so that's your main setup there. So from AS101, it looks very similar. Okay, your local ASN, your remote ASN, and the IP address of router A, which is 102.102.10.2. Okay, router A in AS100. 7.2. Hang on, I'm just trying to figure. Oh, this is for iBGP. Okay, so for iBGP, one thing to note is the AS number. Okay, so even if you're running two instances of BGP, one is iBGP, another one is eBGP, you do the configurations the same way. The only difference is what AS number you're using. So your router is smart enough to know whether it's iBGP when your AS number, okay, here is the same as your remote AS number. In this example, we're both using 100, so this is iBGP. Whereas in the previous examples, we have router 100, okay, connected to router 101, and therefore we are sure, or the router is sure, that the configuration here is for eBGP. Okay, another one for the other connections there, but that's essentially it. How do you now add prefixes? Well, we said that you need to, okay, announce prefixes for you to be reachable. So these are the commands. So for router BGP, you add. There are two ways, of course, to insert prefixes. But what we normally use, at least in my case, is the network statement or the network command. So you specify the network that you're going to announce. In this case, 102.10.32. Okay. This is /23. Okay. And then you need to add a pull-up route. So IP route. For this same prefix, it goes to a specific interface, in this case, serial 0. Okay, so that's pretty much how it works. Same with aggregation. When do you use aggregation? If, let's say, you have many adjacent prefixes, you can announce it as just one bigger prefix. Okay, and you can also use the same command to do that. Now, to check the values, or to check whether you have adjacencies with your neighbors, you can do these commands: show IP BGP summary, show BGP IPv6 unicast summary, or show BGP IPv4 unicast or unicast summary, and should show you the list of your neighbors. These are the ones that you specify, of course, in these configuration. Okay, and then it's the IP address of your neighbors. And then it tells you what version, it tells you the number of messages sent and received between both of you, how long has it been up, and you can see that here. And if the adjacency has been successfully completed, okay, you now will see prefixes, the number of prefixes that is announced to you. In this case, we're receiving 2 prefixes each from our 3 neighbors, 2 for 1, 2 for 2, and 2 for 3. You can also see other values here. It can show as idle, it can show as active. It is idle normally if there are no adjacencies yet. So if, let's say, you've configured it in your case, but your neighbor hasn't configured it properly, okay, or maybe you have set up to connect, or to set up adjacency with a neighbor where the IP address provided is not reachable, so it will just show as idle. It will wait, it will cycle, it will try to send and receive open messages to establish that that connection, that peering with them. But yeah, it will show as idle until it has completed that. It's active if the adjacency is final, but you're not receiving or you're not getting any prefixes from them. If you want to see the entire thing, like in this previous slide, we only see the number of prefixes. But if you want to see all the prefixes that you currently have in your routing table, you can run a command show IPBGP or show BGP IPv for unicast, show BGP IPv6 unicast, and it will give you a list of all those prefixes. And notice these next columns here are our attributes. Next hop is an attribute, which shows that where I would send a packet that I receive if it's for this prefix, so it will be forwarded to this IP address. We also have metrics, okay, MEDs. You have local prefs, okay, local preference. Wait is something that's only for Cisco routers. You also have here your path, because this is for IGP, which you can see with an I value on the left side here. Say, notice the origin code. It's I if it's IGP. So here you won't have IGP there. Your path there also shows I, which is for IGP. You don't see an actual AS path. Unfortunately, I don't have an example that shows you an AS path here, but it will just show you a list of autonomous systems, like their autonomous system numbers in succession. So this will be your AS path. Okay, that is if you are showing here your eBGP neighbors. So that's it. It's just a very brief 1-hour overview of what BGP does and how BGP operates. If you have questions, this is the time to do so. Please write them down on the chat. Now, while I'm waiting for your questions, if you have any, I'm also going to write in or type in the survey. This is the link to the survey here. So if you can please fill that up for me, that will be really good. Now, if you want a copy of the slides, it's also available. Please go fill up the survey, and then after that, it will be not forwarded. You will be forwarded to a link. Okay, it's an FTP site that contains all the materials in PDF format for today. Yep, so that's pretty much it. If there are no questions, I think I will end it here. Thank you very much, everybody, for your time. I really appreciate you coming and listening in for this 1-hour talk. I hope that I can see you in the next sessions as well. Maybe not just now, but in the coming e-learning sessions. If there's anything that's interesting to you, please register them. Have a look at our training website, training.apnic.net. All right, so I'll end it there. Thank you very much and have a good day. Bye-bye.